Hello everyone, my name is Adham Rabi Aziz and I will present to you our work that entitled by Meander Line Slots based Miniaturized Inset Fed Patch Sensor Antenna for Water Characterization Technique. This work was prepared by Khalid, Mahmoud Farhan, Adham Rabi and Raed Abdel Hamid. Also, this work is accepted for publish in the 13th International Conference on System Engineering and Technology. The outline of our presentation is we have introduction, objective, proposed design, sensitivity result, manufacturing and measurement, and finally we have conclusion. The introduction we can start by the main function of the antenna, as we know, is transmitting and receiving the electromagnetic wave. Moreover, or in last decade, there is another function the antenna it was used, which is sensor. This field are gaining growing interest for use in biosensing, microfluidic, environment monitoring, health, industrial, and so on, due to their low-cost, small size, capability to use with wireless electronics, and fast in testing in real time, easy to fabricate. We can handle everywhere, and so on. One of the most common used antenna now is called patch antenna. As we know, patch antenna it's characterized by small size, lightweight, easy to fabricate, low cost, and can embed it with the circuit board. This is the first step in our design, the sensor. Second step is introduced by Meander Line Slots technique that employed and etched out from the patch. The goal of using the Meander line is to enhance the performance by increase the current path in the patch, and as a result, miniaturized in the size, and also the resonant frequency is shifted to the left. The objective of this work is, as we mentioned before, design and analysis highly sensitive microstrip sensor for water characterization technique, which can be summarized, or steps can be summarized by first design the inset feed sensor, second applying the Meander line slot techniques, and finally use or install a PTFE respectal on the sensor. The respectal is used here to contain the water sample that want to be tested. The proposed sensor design is presented in Figure 1, which as seen in Figure 1A, we have the dielectric substrate in gray color that made of from FR4 epoxy of thickness 1 millimeter and length 60, width 50. Then we have the inset feed microstrip line patch connected to the patch, and in the middle there is the Meander line slots. In the Figure 1B, we can see the fully grounded plane that applied here, and finally the respectal that installed is showing in the Figure 1C, which is made from PTFE Teflon dielectric material that characterized by epsilon R 2.2. Before we go to testing the water, we must know something. Each type of water has different electric conductivity, which this can be affected on the sensor performance. First of all, The seawater is characterized by 4 Siemens per meter for seawater. This is electrical conductivity, and 0.01 for freshwater and 0.002 for the distilled water. By using equation 3, we can calculate or evaluate the attenuation for each water type, and we can conclude that the seawater has the highest attenuation value and the highest loss value. In order to calculate the value of sensitivity of the proposed sensor, the equation 456 must be used, where the equation 4 presents the difference in the resonant frequency in case of loaded and unloaded. Equation 5, the difference between the dielectric material in case of loaded and unloaded also. And finally, dividing the difference frequency over difference dielectric and multiply by 100%, we will achieve the sensitivity value. After completing the designing of the proposed sensor by using the HFSS software, then the sensor is simulated and the result is obtained. Here we can see the first test type in case of loaded and unloaded. Loaded is we mean here distilled water in the first test in terms of S11 parameter. The unloaded is present is in the blue curve, and red is in the red curve. From the obtained result, we can see the difference in the frequency location and also the difference between the two resonant in terms of S11 value, which the distilled water has the lowest S11 value compared with the other one that's present by unloaded or empty or vacuum. The second test, freshwater, filled the spectral by freshwater and then compared the result with those in case of unloaded. Here the resonant frequency for unloaded in blue and loaded in red. Also, you can see the shifting in the frequency and change in the S11 value. Finally, we have the seawater filled the spectral, and the result is compared with the unloaded. Here we can see the big change of in the obtained result in terms of resonant frequency and S11 value. Due to the high attenuation of the seawater, we have big difference S11 value. In table 1, all obtained value are presented here in terms of unloaded and loaded. First of all, we have resonant frequency. For unloaded condition, we have 2.74 GHz as a resonant frequency, while when the spectral is filled by dewater or distilled water, we have 2.44 resonant. Freshwater we have 2.49 GHz, and seawater we have 2.5 GHz. Here you can see the difference between the resonant frequency in terms of loaded and unloaded. And finally, the sensitivity value is obtained, which we have 0.9 and 0.75, 0.725 for the distilled water, freshwater, and seawater. And, the next step is presented by fabricating the proposed sensor, where the sensor prototype is, as you can see it in the figure 2 here. On the left we have the proposed sensor prototype without spectral, and on the right we have the proposed sensor with the spectral. And the milling and drilling machine model of LPKF is used to design and fabricate the sensor. The next step is presented by testing the sensor performance, which VNA or vector network analyzer is employed here, and testing the result. We have two tests. First one is when the spectral is filled by distilled water and measured the S11, you can see in a red curve, and then compared with the measurement result presented in blue curve, while the simulation in a red curve. From the comparison you can see a good agreement here. Also for fresh water that filled the spectral, you can see also the measurement and simulation result here, measurement in blue and simulation in red. You can see a good agreement also here. In the both tests you can see an insignificant difference between the simulation and the measurement, where these difference may be some error in the fabricating or irregular soldering defect, some loss due to copper dielectric, SMA misconnected, or something else. The conclusion of our work: first, design and present the patch sensor based on Meander Line Slots. Second, a spectral is installed on the proposed sensor. Third, testing the results, testing the sensor, and see the result that presented by resonant frequency and how is shifted, or the amount or the value of resonant frequency. You can see the first, as we mentioned before, 2.74 for loaded, and 2.44, 2.49, and 2.5 for other type for loaded. The miniaturized sensor sensitivity value is obtained and presented, which is a good sensing value that found equal to 0.9, 0.75, 0.72 for distilled, fresh, and seawater. I wish you a good day, and I wish to you understand the purpose of, or the purpose of this work, and if anyone have a question you can ask. Thank you.